Welcome to this physics tutorial on motion graphs. In this video we'll be looking at the measurable quantities that you can get from a motion graph, the different types of motion graphs, predominantly displacement and velocity time graphs, and we'll examine two worked examples. So first of all, there's a lot of information you can extract or clean from a motion graph. There's three main graphs we'll be looking at, and you're expected to know the first two particularly well in VCE Physics. First one is the displacement time graph, the second a velocity time graph, and the third is an acceleration time graph. Now when examining any graph in physics, regardless of its motion, energy, force, you should always ask yourself, what does the gradient of the graph tell me? And what does the area under the graph tell me? They're two important questions for any physics graphs. First of all, let's look at a displacement time graph. The gradient of a displacement time graph, that is the rise over the run, gives us a measurement of the object's velocity. Here the rise on the vertical axis is measured in x, the displacement, and the run on the horizontal axis is measured in t, the time in seconds. So rise over run represents change in displacement over change in time, which is by definition velocity measured in meters per second. So any point along this red line, the gradient of this displacement time graph can give me a measure of the velocity. So at the bottom point here you have a rather steep gradient, so it's an increasing velocity. Along this point the gradient is less steep, that is, it's decreasing. At the top you have a turning point in a mathematical sense where there's a gradient of 0, so it has 0 velocity at this point. A negative slope indicates a negative velocity or motion moving backwards in the opposite direction. And again, once again here we've got a flat gradient of 0, suggesting the object is at rest at that particular point. That's a displacement time graph. The second graph we're looking at is a velocity time graph. Once again, you should ask yourself, what do I get from the gradient and what do I get from the area? Now the gradient of a velocity time graph, once again, is rise over run. This time the rise is measured in velocity and the run is measured in time. So velocity over time by definition is acceleration in meters per second. So the gradient of velocity time graph gives us the acceleration. So here a positive slope indicates a positive acceleration. A flat gradient of 0 slope represents 0 acceleration, or rather just a constant velocity. And a negative slope represents a decrease in velocity, a negative velocity. You notice here, unlike the previous graph, where our area was not applicable, nothing we can calculate is of use to us, the area of a velocity time graph, by definition of our basic displacement equation, is equal to displacement, because the area is the product of velocity and time, which gives displacement. So if you were to calculate the area under this trapezium, you would have the displacement, the total distance displaced by this object for the first 15 seconds. If you worked out the area under this triangle, you would also have the displacement, a negative displacement, meaning the object is moving backwards. Finally, we have the acceleration time graph. Now the gradient of an acceleration time graph is not applicable for what we're studying at the moment. However, the area is. The area of an acceleration time graph gives me the change in velocity. So if I were to calculate the area of this rectangle, this rectangle, and this rectangle, I could work out the change in velocity. Velocity, of course, is a vector, so I'd have to add my two positives and subtract my negatives to work out my overall change in velocity. Here's a summary of all that information. But importantly, you should be able to see the relationship between the gradients of each of the three graphs. First of all, the slope of the displacement time graph gives us a measure of the velocity. So at this point where the gradient is 0, we find that the corresponding velocity time graph has a velocity of 0. At this point where the gradient is the steepest, we find we have the highest velocity. Here you got a constant gradient, here you have a constant velocity. Here we have a negative gradient and so my velocity is a negative. At this point where I've got a 0 gradient, my velocity is 0. The rate of change of this gradient represents my velocity. There's a direct correlation or link between the two. Effectively, it is dx to t for those static maths methods, rates of change. Likewise, the slope of the velocity time graph provides a measure of the object's acceleration. So here I've got a constant positive gradient. If I can calculate it, it comes out to 4 as a constant positive acceleration. Here I have a gradient of 0, so acceleration is 0. Here I have a constant negative gradient for the velocity, so I get a constant negative acceleration. The value of this acceleration is equal to the rise over the run of this velocity. Here I have a positive constant gradient, so I have a positive constant acceleration. So between each one of these graphs, we have a connection based upon the rate of change of the previous, dx dt and dv dt. Let's look at motion graphs. Two examples. First of all, I have a displacement time graph, and I'm asked 1. to calculate the velocity during the first 5 seconds of motion, 2. to describe the motion between 5 and 10 seconds, 3. calculate the velocity during the final 5 seconds of motion, 4. what is the total distance travelled during the 15 seconds, and finally 5. what's the object's displacement after 15 seconds. So let's look at each one of these in turn. First of all, let's calculate the velocity during the first 5 seconds of motion. So I've highlighted here the first 5 seconds, and we recall from our previous discussions that from a displacement time graph, the velocity can be found by measuring the gradient, the rise over the run. So the rise in the first 5 seconds is from 0 to 60, it's 60 meters. And the run along the horizontal is from 0 to 5 seconds. So 60 divided by 5 gives me 12 meters per second. So we can state the object's velocity is 12 meters per second, and because it's positive, we'll call it in a forwards direction. Second task was describe the motion between 5 and 10 seconds. Well, analysing the gradient, we can see the velocity is 0. There is a gradient of 0. It's completely flat. Now, when an object has 0 velocity, we can say it is stationary. So, from 5 to 10, the object is sitting at a displacement of 60 meters from its starting point. Number 3, calculate the velocity during the final 5 seconds of motion. We can see yet again the rise over run gives us the velocity, the gradient that is. So this one isn't really a rise, it's a fall from 60 meters down to 0. So we have a rise of minus 60 meters and a run from 10 to 15 of 5 seconds. So in this example, the velocity is negative 12 meters per second. We would say the object's velocity is 12 meters per second backwards. Task 4, what's the total distance travelled during the 15 seconds? This is actually a lot simpler. From 0 to 5 seconds, we've travelled 60 meters. From 5 to 10 seconds, we've travelled no meters because it's stationary. And from 10 to 15, we've travelled back a total of 60 meters. Distance doesn't care about direction, and so our sums are 60 meters plus 0 meters plus 60 meters is 120 meters. So the total distance travelled was 120 meters. Finally, what's the object's displacement after 15 seconds? The displacement is comparing the final position, which is 0 meters, against the initial position, which is 0 meters. So in this case, whilst the object has moved out 60 meters displacement, sat and come back another 60 meters back to its starting point, it actually has no displacement whatsoever. It started at a displacement of 0, it's finished at a displacement of 0, and so we say the object has not been displaced. It's finished where it started. Our second motion graph is a velocity time graph. And for this graph, we're asked 1, what is the velocity at the 10-second mark? 2, calculate the acceleration during the first 10 seconds of motion. 3, describe the motion between 10 to 60 seconds. 4, what is the object's displacement after 80 seconds? And 5, what is the average velocity for the entire journey? So first of all, what's the velocity at the 10-second mark? Now warning, a lot of foolish students would calculate the rise over run, thinking this is a displacement time graph. Smart students will see it's a velocity time graph, and to calculate the velocity at the 10-second mark, we simply read across to the graph. So we can say at 10 seconds, the velocity is 20 meters per second forward. Task 2, calculate the acceleration during the first 10 seconds of motion. This is again the gradient. So rise over run of a velocity time graph provides us with a measure of the acceleration. So in the first 10 seconds rather, it has risen from 0 to 20, so it has a rise of 20 meters per second, and it's run from 0 to 10, it has a run of 10 seconds. So 20 divided by 10 gives me an acceleration of plus 2 meters per second squared. So we can state the object's acceleration, not velocity. It's a mistake there, we'll just fix that up. Acceleration is 2 meters per second squared in a forwards direction. Third task, describe the motion between 10 and 60 seconds. Well, from 10 to 60 we have a flat gradient, so there's no acceleration. However, we can see from off the graph that there is still a constant velocity of 20 meters per second. So, from 10 to 60 seconds, the object has a constant 20 meters per second velocity forwards. Number 4, what's the object's displacement after 80 seconds? Now, displacement from a velocity time graph is the area under the graph. We can see the shape is clearly a trapezium, the area of which is a half a plus b times h. A being the smaller width of the trapezium and b being the wider width of the trapezium. So it's going to be a half times 50, which is from 10 to 60. 60 minus 10 is a width of 50, and the larger base is from 0 to 80. So it is half of 50 plus 80 multiplied by a height of 20. So that comes out to 130 multiplied by 20 is 2,600, and then halved comes out to 1,300. So the object's displacement is 1,300 meters forward, just the area under the graph. Finally, what's the average velocity for the entire journey? Well, this is simply, by definition, average velocity is change in displacement over time. The total displacement was 1,300 meters from the previous question, and the time in total was 80 seconds. So 1,300 divided by 80 comes out to 16.25 meters per second. So the object's average velocity is 16.25 meters per second. It's positive, so we say it's in a forward direction. I hope this tutorial video on motion graphs has been of use to you, and once again, thank you for watching.